Good morning, everyone. So, as you can see on the screen, today's topic is damped oscillation. And okay, so damped oscillation, LRC circuit in a way is very similar to damped oscillation in case of spring mass system with some resistance. And spring mass system or mechanical damped oscillation is easier to understand. First, we'll go through mechanical damped oscillation. And then we see the similarity between mechanical damped oscillation with electrical damped oscillation. And electrical damped oscillation is just replacing the quantity in mechanical oscillation with electrical quantity. Let's say this is something if you recall in case of spring mass system, in ideal system when there's no loss of energy, if a spring and mass is connected, there's no friction. And if we displace the mass from equilibrium position, it will keep having oscillation and its amplitude will not change, its motion will be, if there's no energy, its motion will be perpetual. But what is damped oscillation? We know for fact that even if we have a pendulum also, if we give some displacement, it will keep oscillating and gradually what will happen? It will die out. This it comes to a state of rest. And the reason it happens is because in case of pendulum as well as in case of mass connected to the spring also, even if the surface is smooth, there's some, see, because of air molecules, there's a air friction, air drag. So what we assume, damped oscillation, we take the damping force, which could be called as viscous force, as equal to minus B into V. And so what we notice here, the negative sign indicates, and the force is, nature of force is like similar to frictional force. It will act opposite to direction of velocity. So when object is moving towards right, force will act towards left. When it is moving towards left, force will act towards right. That's a negative sign. And force is proportional to velocity. So when it is moving slower, this force will be, dampening force will be less. When it is moving faster, damping force will be more. And this is something we can understand. Those who ride a bike or even in the car also, we can notice, see, when you're driving on a highway, there are also some kind of resisting forces acting. And there are also more than road friction at high speed, which force is important? Air friction. And air friction, you'll notice as the air friction, if you ride on the bike, you are driving at a lower speed, you will feel the force exerted by air on your body is smaller at lower speed, and the speed becomes double. Actually, it is proportional to velocity. And in fact, there's one law also which relates a viscous force or a resisting force exerted by a fluid on an object. You recall any law which has this force related to velocity? Similar to viscous resistance, air resistance. Where do we come across? Stokes' law. And if some of you recall Stokes' law also similar. Stokes' law gives you the resisting force offered by the fluid, which is proportional to velocity in opposite in direction in steady state. This is also something similar. So what is value of B? B is called damping constant. So this is a force which is acting, and B is called damping constant. And what would be the unit of B here? And this is important because see, quite a few questions have come in the past in damped oscillation, and these are simple substitution questions. Only thing you need to be careful with the substitution and units. So what is damping constant here? If they find the dimension of B, it is MLT. See, if I write to find the dimension of B, it would be dimension of force, which is MLT minus 2, divided by dimension of velocity, LT minus 1. So what are we left with? This dimension is SI unit, is kg per second. So if sometimes in the question, if damping constant is given in grams per second, we need to convert into SI unit. So it will be mass per unit. That's the damping constant unit. So any question based on the unit we can spot, yes, this is damping constant. So if we write equation of motion, see, this is equilibrium position. This x is equal to 0. So because of presence of additional force, this equation also gets modified. Equation of motion, we get SHM equation based on solution of equation. Let's see how this equation gets modified. What is the equation we are writing? We are writing equation of laws of motion. What is the equation of laws of motion? Mass into acceleration is equal to, or for summation of forces acting. and we have to choose a direction. What is direction we are taken? Let's say take this x equal to 0, and as we normally do, if I take rightward direction positive, and let's write this equation at a particular instance when it is at position is plus x and it is moving in this direction. What does this indicate? We have taken a particular instance when position is x, which is also positive, and velocity also is positive. In this case, can we mark the forces? This is how the object position is. Can we mark the forces here? Two forces will act at this state. What are two forces which will act at this particular time? The spring force, since the displacement from mean position like this, the spring force will act towards left, and viscous force also will act towards, or damping force also will act towards left. How does the equation write? The spring force is minus kx and the damping force is minus bv. So that's my equation, and you can write for any position, equation will come similar. Okay. So we just okay. So you transpose this quantity. That's the equation of motion. And if people have not done differential equation, and anyway, this is second order differential equation. This is not part of our syllabus even for your competitive examination. So we don't go for solution. We simply write the solution and verify the solution is valid or not. What is the solution of this equation? Equation is somewhat, there's some similarity and dissimilarity with SHM equation. So this equation here. So what we find, this term looks similar to my SHM equation. And this term is called oscillating. So this term is periodic. And this term is called amplitude. But in case of SHM motion, amplitude term will come just as A. Here, this amplitude has come as a function of time. The only difference, there are two differences here. This omega will not be same as typical SHM motion. And amplitude also, unlike the normal SHM motion, this amplitude also keep on reducing. So based on our understanding, also yesterday we were talking, what is likely to happen? If because of friction, we expect, even before we start the solution, we expect this amplitude to keep diminishing with time. And this expression indicates, yes, amplitude will keep diminishing with time. And second thing, we expect time period to be greater than time period without dampening. So time period will increase. It will take more time because of resisting force which is acting. So time period has to increase or omega has to decrease. So this omega, what we get here, should be less than omega naught. What is omega naught here? What do we refer to as omega naught? Omega naught is angular frequency of oscillation, which is root of k by m in case of undamped oscillation. So compared to undamped oscillation, what is undamped oscillation? And b is equal to 0. You notice what happens when I substitute b is equal to 0, this term becomes equal to a. So compared to undamped oscillation, its amplitude will keep on diminishing. Amplitude is not constant. And second thing, compared to undamped oscillation, time period is greater, angular frequency is lesser. Omega will be lesser than omega naught. So what is omega naught? That we'll write here. That's a solution. And what are the terms here? B term is damping constant. And unit of this will be equal to kg per second. That's SI unit. And omega also, we can actually substitute and solve. There's no need to go into solution. But the solution for omega also comes like this. This k by m minus b by 2m square. Here also, if you substitute b is equal to 0, what does it reduce to? If b is equal to 0, it reduces to, for b is equal to 0, omega reduces to omega naught, which is equal to root k by m. What is this term k by m? So I can understand k by m. Actually, k by m is nothing but omega naught square. K by m is angular square of angular frequency for undamped oscillation. So we'll write this slightly different form. This is something looks up. And when you look at this b by 2m, this term is same as b by 2m here also. This term is coming in amplitude. It is also coming in case of angular frequency. So rather than b by 2m, I'll write in simpler form. So common term what we use, so even b by 2m also, I can use a term called gamma. And unit of this term unit will be same as k by m. And k by m unit is, okay, so b by 2, unit of b by 2m will be equal to same as square root of k by m, or unit of b by 2m will be same as unit of omega, which is per second. This is gamma unit. Gamma is b by 2m, is nothing but substitution. So is there great understanding? Not great understanding. This is important to understand the method. This topic is more of use of formula and method. So I can rewrite this equation in this form. It is e raised to power minus gamma t. And what is omega here? Omega also can be written as this term as omega naught square minus gamma square. All we need to remember, omega term we know already. We should remember the gamma is equal to b by 2m. So this becomes a simpler form. And that's a form which we need to make use of. So amplitude of oscillation decreases exponentially with time. So the properties of exponential function will apply. Something like this. So compared to what we notice here, yes, omega has decreased and t has increased. So this omega definitely is less than omega naught. Omega is lower, hence time period is higher. So compared to undamped oscillation, damped oscillation, time period increases. And if we observe this, how it will be. So from here to here, what is the time from here to here? This is time period. From here, this is second oscillation time period. This is third oscillation time period. So if we calculate this T1 will be equal to T2 will equal to T3. It means time period of oscillation remains constant, which is less, which is greater than T naught. But what we are looking at the amplitude here, amplitude will keep on diminishing. That's what, and if we connect all the points here, this will, all these amplitude points will lie on a curve which is of nature e raised to power minus gamma t, exponential decay. So exponential decay, we'll look at this. Yes, Akash?
So it still oscillates forever, but only the amplitude decreases. Right?
Yes, but after some time, what will the amplitude of oscillation? Amplitude of oscillation goes to zero.
Okay.
Something we say in case of see like LR circuit. How much time the charging takes in QC in terms of capacitor RC circuit? What is the charging time? Infinity. But still the major portion, 99.9% of charging gets over in a very finite time. So this also, it will continue for infinity, but amplitude becomes so small, it will barely be observable. Anybody else has any question?
Sir?
Yes.
So can we explain why the time period will remain constant, like without the equation?
No, you can't. Even
Okay.
that's not so easy, I'm saying. So this something can be intuitively tell. If you understand, logic remains very similar to in case of undamped oscillation. Why undamped oscillation time period is same, despite the distance is more? Because when the distance is more, and when it is compared to lesser amplitude, the force is greater, acceleration is greater. It is similar to something like this. If there are two things here, one is having a smaller amplitude and one is having larger amplitude. Same pendulum, smaller amplitude, larger amplitude. It is equivalent to from extreme position. This will start with lower acceleration. This will start with larger acceleration. Both will end up reaching at the same time. Actually, similar logic exists here. Here also the restoring force again remains proportional to displacement. In addition, one more force has come and that does not affect the time taken. Okay, so intuitively it makes sense. There's some similarity, but can we just prove by logic that it will remain constant? No, we cannot prove by logic. Not everything can be proven by logic. So a mathematical solution also has its place. Yes, Alan?
So if we take frictional force as the opposing force, then when it comes
No,
to
okay, sir, just keep in mind, are we taking frictional force? We are just calling it not frictional force. We are calling it damping force. What is the nature of force? Force is proportional to velocity. Don't go on beyond that point. It's not a frictional force. It's a damping force, which is proportional to velocity. What is something perhaps more closer to kind of force minus v omega? The resistance is more similar to this kind of force. So think of not in terms of friction, as I'm beginning as I said, frictionless. Which force? This force is like a viscous force or air resistance force. So this damped oscillation, why we are taken like this? You see, if we have a pendulum, it comes to rest. So which force is dominant dampening force? Something like air resistance. The force is proportional to velocity. Okay. So similar to this equation. And what is the energy of oscillation? Energy of oscillation we compare to spring mass system. Energy of oscillation can be written as 1/2 Ka square. Of course is not changing. So as the amplitude is changing, energy also is changing. So if you write energy function as a time function, energy will become equal to 1 by 2 ke raised to power minus 2 gamma t. So their energy will drop more rapidly. So when amplitude becomes half, energy will become 1/4. When amplitude becomes 1 by root 2, energy will become half. That's the understanding we have to make. See, this is something I'm just explaining formula, which need not, which I should not perhaps, but just what the formula is. Now we talk about, I think we don't go into too much of detail. There's something called over damping. Actually, this derivation, why we don't go into derivation of this formula? This derivation is better understood using complex number and linear complex number combination and all. I think that becomes a little complicated. And this derivation is taught in first year of engineering courses in most places. When you have better understanding of differential equation and complex number. So basically, when you say when over damping, what happens? Let's look at the equation. What will happen when gamma is greater than omega naught? It's called over damping. If gamma is greater than omega naught, what will happen? Sorry, I didn't write that equation here. When gamma is greater than omega naught, yes, it's possible. That value b by the gamma value is b by 2m. It can be greater than omega naught. If gamma is greater than omega naught, what will happen? This what will this term be? This term will become imaginary. What does imaginary imply? That's called over damping. So when we talk about over damping, when gamma is greater than omega naught, the motion becomes non-oscillatory. Is something like this. If you want to understand viscous force, just assume one is we can make this pendulum oscillate in air where damping is small. Air doesn't offer great resistance. But just assume that if I take a pendulum here, which has a bob here, rather than making it oscillate in air, I keep a container here which is filled with something like honey, and I take it, which is highly viscous. So if it is honey, what will happen? Which term will increase? So whatever term we have come across compared to air, which term, we have talked about several terms here. Can somebody tell me which term will increase if I have in place of air, if I have honey? Which term will increase?
B.
B will increase. B will be much higher. And gamma is equal to B by 2m. If B becomes very high, the gamma becomes very high, and it may exceed omega naught. Just think of it, what will happen. If it is highly viscous grease or something like this, if I take the pendulum here and release it, what may happen? It may offer so much of resistance, it will very slowly from here and come to rest. It will not even oscillate. So that is over damping. I think over damping, this is also understanding the formula and little bit relate the formula to a real life scenario. Does it make sense if I make something like this highly viscous rather than, see, air also is a fluid, but air in case of B is very small, and hence the gamma is very small here. Thus, those is called under damped oscillation. Over damped is non-oscillatory. I think reason is, and you have to think of over damped oscillation. That's an example of over damped oscillation. Even in the car also, you see, when you have spring also something like this. So what kind of damping we use in the car? In the cars also we use over damped oscillation. Because why we use over damped oscillation? If it is not over damped, if your car passes through one bump, what will happen if it's not over damped? You will keep oscillating in the car, which is not comfortable. So the shock absorber in the car also are designed for over damping. Okay. So this is something I'm just relating this part here, since energy is proportional to square of the amplitude. So we can understand when amplitude becomes half, energy becomes 1/4 of the initial energy. And when energy is half of the initial energy, amplitude has to equal to 1 by root 2 times the initial amplitude. We call something as half-life. I think some of you recall, might have done in the same thing in case of in the chemistry also, radioactivity. What do you define as half-life? Suppose I define half-life as time for amplitude to become half. Understand how much time is taking for amplitude to drop. If I define this half-life, so what is amplitude? So this is the time. So in this equation, if amplitude is substituted as what is the time it is take to, if I calculate value of t here, this is half-life. And if I simplify this equation, I put a suffix here 1 by 2. Indicate this is spatial time. What is the spatial time? If I rearrange this term, this half-life comes equal to ln 2 divided by gamma. log to the base E, log to the base E divided by gamma. That's half-life. Have you done the similar equation? Do you recall similar equation in case of radioactivity in chemistry?
0.69 into
And value of log 7 is 0.69, and actually most cases either you can take a 693 by gamma, and or maybe you can many cases we can approximate as 0.7. So that's a half-life. And if you recall, and see other thing, the property of, okay, so we come to this part. So this is, so in terms of what is damped oscillation, what have we understood about damped oscillation? In case of damped oscillation, we said, okay, in addition to conservative forces, there is some viscous force also is acting, which is proportional to velocity and opposite to direction of motion. That's a typical behavior of a viscous force. We add one more thing here. It has two effects. What are two effects it has? Damping has two effects. What are the, in terms of understanding, what we should understand, what are the two effects damping has? Amplitude will keep on reducing, energy will keep on dropping. That's one effect. And what is the second effect? Omega will decrease, time period will increase. And that's what we capture in terms of equation. That's the two effects of damping. And value of damping constant of this damping constant is B. And value of gamma is equal to, you should remember, gamma is equal to B by 2m. And what was unit of gamma? Unit of gamma is equal to 1 by t per second. And gamma, and so we should remember this term, and we should also remember value of omega in case of damped oscillation. And yes, if you want to remember also, a little bit easier, I can write this same term as like this. This is the normal omega naught equation. Only thing what I do from here, I'll subtract something. What is something we subtract? Gamma square. It becomes equation for gamma or omega. I hope I all relate to. So if we try to memorize the formula with some understanding, it becomes a little easier. So this is same thing, omega, I write K by M, which is the formula for damped oscillation. Since omega gets reduced, I need to subtract some quantity. The quantity what I need to substitute is equal to minus gamma square, gamma is B by 2M. So these are two formulas we have to make use of. And all numericals which have come in the past also can be solved on this basis. Okay, now coming to why are we discussing this topic again? This is for SHM topic. The reason we are discussing here, we talked about our LR circuit. LR circuit also, in that case, we compared LR circuit to a spring mass system. This L is similar to mass, and it was equivalent to 1 by C. And here also there's no loss of energy. But as I said, in case of mechanical oscillation, loss of energy is inevitable. Similar way, whenever you have electrical circuit, it is impossible not to have any resistance. Any wire will have resistance. So there'll be some resistance here. So any realistic oscillation, LC oscillation, there has to be resistance as well. So here also similar way, and we find this has a lot of similarity. This is something is difficult to intuitively understand. Mechanical oscillation is relatively easier to understand intuitively. So what we do here, so again what we'll do here in this case also, if let's see, so there also what we do, there we give some deflection. Let's say this one is given some initial charge Q0. And you remember how do we give initial charge? And after giving initial charge to capacitor, a resistor and inductor both are connected. So what will happen moment you give the charge, moment this connection is made, charge will start flowing. Charge will move from positive plate, try to move from positive to negative plate, it will tend to move like this. So as soon as this also similar to RC circuit also, it will establish current, and it will also lead to EMF generation across L. So let's see, so at time t, what we do, so this is the initial charge given, this is the initial charge given, and at some time t, at some random time t, we assume here the charge has come down from Q0, the charge has become to Q value, and at that instance, yes, we are talking about discharging phase. It is discharging. So current also will be flowing like this. This is the current. I is the value of current. And will the current be increasing or decreasing here? During discharging phase, we have done that part. Current will keep on increasing. If the current will keep on increasing, there will be EMF induced here, and it's like this. So at this stage, at random time t, if I apply Kirchhoff loop rule, how would I write this equation from here to here? Increase in potential by C, moving from negative to positive plate, minus L di by dt and minus R. So basically, this is the any EMF, and depending on how I is varying. But in this case, when I write what is value of I here, I is, I think we had done it earlier in case of LC oscillation also, is minus dq by dt. This current here with this sign convention is rate at which charge is decreasing. If I substitute I here, this equation I get here. And then when I get this equation, I compare with the equation of mechanical oscillation. This was the equation in case of spring mass system with a viscous force. So what I notice here, these equations are almost identical. Only thing in this case, in case of M, has been substituted. What is R in place of B? If I substitute R, and in place of K, I substitute 1 by C. So typically, any book you refer to, you will not find many questions on LRC oscillation, but all LRC oscillation can be solved as mechanical oscillation by substituting L in place of M, R in place of B, and 1 by C in place of A. So whatever solution I had for this equation, the solution was for between X and T here. Here the solution will be between Q and T here. And what was the natural solution? This is the equation, similar to the previous one. So charge will vary, and what does the Q naught indicate? Amplitude of charge. So again, initially the maximum charge given was Q naught. After completing one cycle, will it again acquire a charge equal to Q naught? No. After completing every cycle, the maximum charge will keep on diminishing in the capacitor, and energy of the whole system also will keep diminishing, similar to the previous case. So this equation, and what is gamma here? Okay, omega naught, again if you substitute this value, omega naught is 1 by root LC, and gamma in place of there was B by 2M, it will become R by 2L. Similar substitution, rest all is same. Okay, so that is how do we use LRC oscillation, and here also energy will keep diminishing, and something similar here. Let me look at some questions based on this concept here. So let's start with simpler one. Now, a particle is performing oscillation in the frequency of 5 Hertz. After 10 seconds, its amplitude becomes half. What is this second is what you may also call as half-life. So 10-second amplitude has become half, or we can say in 10-second energy has become 1/4. Then find the time taken from the start for amplitude to become 1/4 of the initial value. How much time will it take to become 1/4?
20 seconds.
20 seconds. So this is something all of you can do. So every 10 seconds, it will keep becoming half. So from 0, if it was E naught, is equal to 10 seconds. This is 10-second time interval. It has become E naught by 2. For next period of interval of 10 seconds, again the beginning amplitude was A naught by 2. End of the same time period, it will become half of the amplitude at the beginning of the interval. It will become E naught by 2 by 2, which is E naught by 4. Total time. So that's how we have. So every half life, amplitude becoming half. And it's not only valid for something else, but okay. Let's look at this question. And as you notice, I'm solving all the questions which are related to mechanical oscillation. The questions which have come are mostly about mechanical damped oscillation, but very likely, if you'll notice, the pattern keeps changing. Quite likely, you may have similar questions on LRC oscillation. But LRC oscillation also, we can solve exactly like a mechanical oscillation by substitution of making suitable substitution. Let's solve this question here. And we'll just solve it's a mathematical question. Okay, so what is time period of oscillation? So all we have to do, I have to use the, okay, I have my formula for omega. Omega formula is what? Omega formula, how do I remember? Omega formula is same as we have undamped oscillation. Omega is root A by M minus gamma square. I'll calculate omega and then I'll calculate time period. So let's do that. That's my formula, omega naught square minus And this term is nothing but omega naught square minus gamma square. Let's put this value here. What is omega naught? K by m. What is k? K value, we substitute 80 divided by 0.2. We get omega value. And what is gamma value? Okay. And can we calculate gamma? What is gamma equal to? Gamma is equal to b by 2m. B is what? Is B 40 here? Only thing you have to be careful. So first of all, when you check, is this same as B? Yes, is mass by time. So this is B, but B is 0.04. What you need to substitute B as 0.04, all SI unit. I get gamma is equal to 0.1. So time taken, so time period of oscillation, I calculate omega, I can easily get time period. Time period will be equal to 2 pi by 20. That's the time period. That's pi by 10, so 0.314 second is my time period. What is the time it will take for amplitude to drop its initial value? This equation I have used. I'll calculate value of T. Or I know this is nothing but half-life. Half-life is ln 2 divided by gamma. So I'll calculate value of gamma. Gamma comes to 0.1. So I substitute those value, I get my answer. So this T will come equal to 0.69 divided by 0.1. It will come equal to 6.9 seconds. There's nothing, simple substitution. And time for energy to drop to the half is initial value. If energy drops to half, what has to be amplitude? In that case, amplitude has to be equal to A naught by root 2. You can calculate that time also. And that will come to little odd term. Let's look at the questions. Some of the questions which have come are a little tricky also. This is one of the difficult questions which has come. And unfortunately, the question which had come also did not have exact answer. But let's see that one. This is if you understand this question, I think this is one of the more clear question on damped oscillation. Amplitude of simple pendulum oscillating in air. Smaller decreases from, so 10 to initial amplitude was 10. In certain time it has dropped to 8 in 40 seconds. Assuming Stokes' law is valid, the ratio of coefficient viscosity air to that of carbon dioxide is 1.3. What I'm saying now, so first it is oscillated in air, and then same thing was oscillated in carbon dioxide. Should it lead to any change if I oscillate in air or if I oscillate in carbon dioxide? Why should there be any change in equation?
Damping constant.
Damping constant will change.
Proportional to viscosity.
Proportional to viscosity. So this question was only to understand, see my damping force. What is damping force equal to? Minus B into V. Here they are saying Stokes' law is valid. Viscous force is my damping force, which is 6 pi eta RV. Nothing else is changing. Only thing which is changing is coefficient of viscosity. So if I have some value of damping constant for air, if viscosity decreases, B will decrease. If viscosity increases, B will also increase in the same proportion. That's the only thing. Rest all is formula. Let's see how do we solve step by step. So basically for air, and this is something this of carbon dioxide, what is given here? Viscosity is given. So if this value is eta, for carbon dioxide is eta divided by 1.3. So whatever value of gamma I have for air, the value of gamma in carbon dioxide will become gamma divided by 1.3. That's the only thing we have to take into account. Okay. So B will get reduced in the similar proportion and gamma also reduced in the similar proportion when it is oscillated in carbon dioxide. So these two things are given. So one case is when it is air and what is in carbon dioxide. So this case, when I substitute in air, I'll use value of gamma here. And when it is for this particular case, when it is oscillated in carbon dioxide, I'll use gamma divided by 1.3 in place of gamma dash equation. That will be gamma for, you can say gamma C, and this is equal to gamma A. Now rest all is substitution. Let's substitute those values for air first. So this air, what is the equation? Which equation? We are going to use amplitude equation. This is what is the equation? You are using say amplitude after time t is equal to e raised to power minus gamma t. You know, that's equation. What is after time? After t squared, just substitute t equal to 40 here, and this is 8 and this is 10. They're same. If we there's no need to change unit, it will cancel out anyway. So this is one equation for air, and from air we can get the value of gamma. So what is the value of gamma we get from here? So this equation I could have written as A is equal to e raised to power 40 gamma is equal to 5 by 4. Or we take the log of both sides and rearrange the term, you will get gamma as this term here. Okay, that's a for air now. Now again, I have used the second equation for carbon dioxide. For carbon dioxide, what is the equation now? This is initial amplitude. This is the from drops from 10 to 5 value. Only thing what we have done in place of gamma here, you have to use gamma divided by 1.3 into gamma t, and we need to calculate the value of t. All we need to do is substitute the value of gamma from here to here. Rest all is simple simplification of this term. So what do we get here? So again, if you write what is e gamma raised to power 1.3, this term, it comes equal to log 2. And put the value of gamma, substitute value of gamma as 1 by 40 log 5 log 3, and we simplify. What is this term t comes to? You can simplify this term, and in this exam, value of these two terms were given. Only thing, okay, and you can simplify, it comes equal to 167. So this was a question, and this question, actual option given the examination was 162. And this one doesn't come very close to 162. Actually, it comes closer to 167. But since other options were not very close to it, this was the right option, which was this actual means question. But I was just checking how the answers have been given. I find some of the sites, even Topper and some other Doubtman and other things, they are given this option is correct, which is not correct. This option only is correct. Actually, the value comes closer to 167. So they have marked 162 as the correct option. Forget about how it has come, what error was there in the question. You should understand how to solve it. It's a simple substitution. Is this understood? Priya?
Yes, sir.
Okay, so again, if I ask damped oscillation, what are the points we should, okay, if we ask you to list out what are the key points we should understand in case of damped oscillation, can you tell me what those key points are?
Amplitude decreases.
Amplitude keeps decreasing with time. And what happens to compare to see what we do, damped oscillation we can compare to undamped oscillation. So amplitude keeps decreasing with time. And what is the second change which happens?
Omega decreases and time period increases.
Omega decreases and time period decreases. And how does it, so if amplitude decreases with time, I should know the formula. How does it vary with time? What is AT equal to as a function of time? It keeps decreasing. And this is something no choice but to remember formula. It decreases gamma t. Second thing what we remember, see, when we talk about damped oscillation, first thing our should come to our mind, in case of damped oscillation, there is a damping force. What is damping force or viscous force equal to? That viscous force we define as minus BV. And because of which two things happen. So let me repeat, what is damped oscillation? Damped oscillation, in addition to normal forces, a damping force also starts acting. And we solve only for one condition. The damping force is minus BV. If that's a force, amplitude of oscillation as well as energy of oscillation keep diminishing with time, and time period increases, omega decreases. So only thing I need to know, what would be the amplitude which will vary with time, and what will happen to omega. So omega also, how do we write? Omega also we can write, okay, omega is same as omega naught minus something. Minus how much? Omega is gamma square. So only thing in terms of formula what I needed to remember, this thing, and gamma is equal to B by 12. But last point what you need to remember, how is it related to electrical circuit? Electrical circuit we just simply substitute in place of mass, we substitute L. In place of K, we substitute 1 by C, rest all remain same. So these are points we need to remember. And damped oscillation, can we derive? No, we can't derive because its derivation requires solution of second order differential equation, which is not in the syllabus here. Only thing, intuitively we can understand these 2 points and we take these values as given. Yes, Ahlad.
So what is the purpose of the small spherical box here?
What is the purpose of?
Why did they mention it's a small sphere?
In this question?
Yes, sir.
Small spherical ball. Okay. Okay.
So Stokes law is valid only in case of spherical balls, right?
Yes. First of all, that is valid for a spherical ball. And actually, in this particular case, I don't think it's a great significance. Okay. In case of in case of Stokes law also, suppose I take case a bucket. I think I mentioned there also. If you take a very tall bucket of great height, it's a deep bucket. If I drop a small piece of iron, okay, and suppose I drop a large piece of iron, and I apply Stokes law in both cases, if the piece of iron has a large radius, it is valid only for a small radius. You know why is it so? I think I mentioned in case of Stokes law.
The pressure difference.
No. Whatever is this was is large, it will be, see, if this is small, it will not lead to, see, if you just imagine it's a very large ball, what will happen as the ball moves down, the liquid also start moving up. There is relative motion between liquid and ball. But a small mass, that won't happen. Okay, so only thing, so the mass is not so large that it creates the velocity of the liquid also. Okay, otherwise, in this particular case, has no significance. If it is slightly larger also, it will not have made any difference. Okay, this question is purely mathematics. Understanding of small variation. This also is a past mains question. All of you read the question and see how do we solve. This question is, I would not put this into damped oscillation category. I'll put into questions of experimentation and errors. We have done some question on errors. This is more on errors. Let's see how do we solve. Similar concept, small changes. Change in time period, approximately how much. Just read the question and see how do we solve. So I'll give you a couple of minutes for all of you to think how to solve.
Problem in these errors kind of questions. Yes. Yes.
Okay. So this is something, see, we have, this is how omega found it. What we need to do here, this ratio is given. We have to calculate change in time period compared to undamped oscillator. Okay. How is, we know the formula for omega, but are time period and omega related?
Yes, sir.
Time period and omega related. First thing what we notice here is since T is equal to 2 by omega, in terms of small changes, I can write percentage change is equal to minus percentage in omega. This, all of you understand this part, no issue. So this is the quantity I could write as delta T by T or dt by dt is equal to minus delta omega by omega. So I'll calculate percentage change in omega. Negative of that will be percentage change in P. Because percentage change in omega is easier. Both are not so different. So what is omega here? Omega percentage compared to omega naught. I'll take this term out common. Why am I taking this out? Because so that get omega naught, I've taken this term out as common. What is left? This is the term which is left. And okay, so this equation, this is, and this is omega. So this equation, this omega is equal to omega naught. And what is this term here? This term is 1 minus, this value is given. So this value is equal to 0.08. R squared by mk is equal to 0.08. This whole term is given as 8% or it is equal to 0.08. So 0.08 by 0.04, it is equal to 0.02 raised to power 1 by 2. So in essence, all this information is given here. It comes to this relationship. Now, can I find a percentage change? This omega, what is percentage change? This spot, what is the percentage change in omega now? This one is equivalent to, so when we have, this is again approximation. So this is small quantity raised to power, this is equal to, it implies omega is equal to omega naught 1 minus 0.01. Or omega is decreasing by 1%. Omega decreases by 1%, it will increase by 1%. Or if those who are not very clear, we can also write this is omega naught. So if I have to write what is percentage change in omega, how do I write percentage change in omega? Omega minus final value minus original value divided by original value into 100. Do I get omega minus omega naught here? From this I get value of omega minus omega naught. Omega minus omega naught will be equal to minus 0.01 omega naught by omega naught into 100. So it decreases by 1%, hence time period will increase by 1%. So does it involve any physics? No, it only involves manipulation of small changes. And this is something you pay attention to. all of you, those who are not very clear, I expect all of you to go to this question 2-3 times. Make sure that you understand the basic approach required to solve questions involving small changes. This is a very common type of question. Very often, every paper you may get one such question like this. Tejas, is this understood?
Yes, sir. Yes, now I
Is
understand.
that difficult one?
No, sir. I should have got one.
That's okay. So
Yes,
that's
sir.
something, and we should always remember how to deal with small changes. The moment you look at the number, all or anything less than 10%, we take it as small changes. We can solve like this. Okay. There's some question. They are much simpler. These are part of exercise. All of you can solve those questions. So the previous questions, what we have done, are the questions which have come in the mains also in the past in damped oscillation. So though we are in the topic of LRC oscillation, I have gone through damped oscillation, mechanical oscillation. That is something both are exactly the same thing. Only thing we replace one quantity with other. We understand mechanical oscillation, which is slightly easier compared to electrical oscillation, and we can solve question on electrical oscillation as well. Okay, then there's small topic of transformer. Okay, let me go to the topic of transformer. What does transformer do? I think most of you must be familiar with the function of transformer. The function of transformer, and then we see the need also. Why do we need to change? It changes the voltage of an alternating current. And which principle it uses? It uses the principle of mutual induction. And if we have to draw up a very simplified version of a transformer, the transformer, it has something kind of like an iron core. Iron is bent in this shape, and this is one arm of the iron core, the second arm. So there's something input. The purpose of it, there's something here. On one side you have input side, and other you have output side. Input side we call as primary, and this we call as secondary. What we expect here this side has some voltage, this side will have some voltage. So what we do, this input voltage is not equal to output voltage. Sometimes we want to increase the voltage, sometimes we want to decrease the voltage. So whenever we want to convert the voltage, we use a transformer. And we'll briefly look at why do we want to convert. So what does it do? It uses two sets of coils. Primary coil we call as input side, and secondary coil we call as an output side. Okay, and it has certain number of turns. Okay, you see here. And what else we have here? These coils are wound in a soft iron core, so that typically, let's understand one more property of iron core. See, if we have a solenoid, this coil is also like a solenoid. If solenoids are wound like this, how are the field lines due to solenoid? All of you recall what is the shape of field line due to solenoid? Very similar to field lines, maybe something like this. This is how the field lines due to solenoid are. Now, if we place a magnetic core, if we place an iron core, suppose within the solenoid, this is how the field lines were. What happens if we place an iron core, long element, it goes like this, much longer than solenoid. It has two things, again, unfortunately, for some reason we have not done that mechanical. If this we place an iron bar, it modifies the field. What it does, there are two things happen because of iron core. Two things. What are two things will happen? First of all, earlier the magnetic field which was equal to mu naught Ni, it becomes mu Ni, which is in case of iron, this value becomes much higher, similar to dielectric. This B becomes much higher. How many times higher? Actually, in the order of hundreds times higher. B becomes higher. So field lines earlier, if there were 10 field lines, suppose we draw 10 field lines inside the solenoid earlier. Moment I place a iron core here, then it will become hundreds of field lines. So B becomes more higher magnitude. And second thing, one more thing happens here. See, earlier what was happening, as soon as the solenoid gets near the end of the solenoid, field lines will go like this, spread over all over the place. Field lines will spread out. Moment to create an iron core, it confines the field line. It channelizes, it confines the field line. So, moment I place the iron core, here also field line will not spread out. field lines will run all through like this. It attracts a field line kind of thing. So it doesn't let field line to escape. So here also, this is something, if I look at this, here also field lines are there. The field lines, so how the field lines will be, it will confine all the field lines within its core. All field lines will run like this. I think the figure is not very clear, but field lines are like this. So whatever field lines are there within the primary core, those field lines also, can they escape? No, it will remain within the iron core. That's how the field lines are. Second line confines the field lines. The effect of iron core is whatever number of field lines are there in primary coil, same number of field lines are there in the secondary coil, which means flux per unit turn is same in the primary coil as well as secondary coil. This is what happens because of iron core. So I am all this story short, cutting all the story short. What does it do? It makes sure iron coil is wound on a server core so that magnetic field lines are confined within iron core. Hence, flux per unit turn. Let me define a term called phi. Unit turn is same for both, all turns, but all coils, if you take each one as one turn, any one turn if I take either in primary or secondary, flux through each turn is same, or I am saying the total flux to the primary coil will be equal to I into number of turns. That's it. What is the flux in the primary coil? If primary coil has NP number of turns, flux through primary coil will be NP into phi. And the secondary coil, what does NS indicate? Number of turns in the secondary coil. And how do we use a transformer? By making this them unequal. We see that part. So what is EMF in the primary? As the current here also is alternating current. So this also current will keep changing, as the flux also will keep on changing. So EMF in the primary is the rate of change of flux will be equal to, if I take d by dt of this, this term is same. We typically write minus L induced EMF is equal to minus d phi by dt. So EMF in the primary is equal to minus NP into d phi by dt. Similarly, I can write EMF in the secondary also, which is plus d phi by dt. So what we notice here, what is the relationship between two EMFs in the primary and secondary? EMFs in primary and secondary are proportional to number of turns in the primary and secondary. That's the only point the key point in case of transformer, a very simple point. So EMF on the primary and secondary ratio is same as the ratio of number of turns in the primary side and the secondary side. Okay. So let's continue further here. And for ideal transformer, when we feed, okay, one is voltage, and second thing actually transfer of energy. For ideal transformer, we assume there's no loss of energy. So current into voltage, which is VI, which is the power on the input side, is equal to current and voltage in the output side. For ideal transformer, IS into VS, current in the secondary and voltage in the secondary, is equal to IP into VP for 100% efficiency. So here, if we substitute those terms also, the ratio of current is inverse to ratio of voltage. So if we combine all three put together, there's a relationship in case of transformer. Voltage is in proportion of turns and current is inversely proportional of turns in case of 100% efficiency. And we call something as step up transformer. In case of step up, as the name suggests, we want to increase the voltage. Voltage in the secondary is greater than voltage in the primary. It means number of turns in the secondary has to be greater than number of turns in the primary. Where do you use step up? Step up is used at the generation plant. After power is generated, it is transferred from point of generation to point of consumption over a large distances. So when the power is transferred, you would have seen those transmission cables. Those transmission cables, it is transferred at a much higher potential. So what we do, point of generation, using step-up transformer, we have something like 11 kVA and all those things, well, very high potential. So 11 kVA and something. So it transferred at high potential, and we use a step-up transformer. And why do we increase the potential for and is transmitted? Minimize transmission losses. But before we consume it, either in the industry or at home, we again bring it down to lower potential for safety. Okay, so power generation is also not very high potential. Consumption also not high potential. Only the transmission takes place at high potential. This needs step up and step down, and many other applications also. Many other applications also do the same. Okay, so that's why you need step up. And if you read, some of you read about history also, and there were a lot of debate about whether initial, when electricity was slowly gaining popularity as important source of energy, a lot of debate whether it should AC and DC, which one is better. And one of the key benefit of AC was it is very easy to change the voltage. And even at the home supply also, even charging battery and all this, you notice whether those things, it can reduce the, so even those chargers and all also work as a transformer as well. So in case of, and this mutual induction, the principle what we use is possible only when the current and voltage are oscillating. It is possible only in case of AC. And this is a basic equation, very simple. But in case of real transfer, okay. In case of real transformer, we'll have losses. And if it is losses are there, efficiency will not be 100%. I think typically the efficiency range from something like, most transformer has definitely more than 95%, and typically 95 to 99% efficiency. So whatever energy you feed in, we look at what are the losses. Reasons for losses are flux leakage. Magnetic field also is a form of energy. If we assume that iron core is able to make sure that all field lines which are generated remain confined within the iron core and reaches here, but some of the field lines may escape. But the field lines are actually, some field lines are not within this. So we don't have to go in more detail and no further theory, but yes, there's some leakage of flux. Some magnetic field lines are not put to use, they escape in the atmosphere. So when a field lines escape, magnetic fields are not put to use, magnetic field also is energy. There's a loss because of flux leakage. There's also some heating takes place because current is flowing in the primary as well as secondary. And whatever wire we use, it will always have some resistance. And if there's resistance, there's some heating effect and there's a loss of energy in case of resistance in the winding. And the third thing is eddy current. Eddy current I will discuss tomorrow. Eddy current is a small phenomena. We had not discussed earlier. This is in part of EMI. But there is a application, first time we come across application of, not much, it is also just 2 minutes topic. Its use comes in case of transformer. So here we'll understand what is eddy current, which is based on principle of EMI. So I'll stop here and we'll continue with the transformer tomorrow as well. Okay. So